design of truss bolted and welded connection. Just a quick reminder, during the last few weeks, we learned that we maybe have main system called truss with different members. This main system is repeated at equal spacing S. We are able to calculate how much dead load, how much live load, how much wind load at each joint of your truss from your layout. We are able to analyze this truss using RISA. We are able to get the internal forces in each member, which is maybe in tension or compression. We are able to design your tension member and compression member as well. Today, we will talk about what is the connection design. Your connection may be welded connection, may be bolted connection. So if your connection is bolted, how many bolts? If your connection is welded, what is the size of your weld? What is the length of your weld? So all of this stuff we need to cover this week, design of connection. In truss, failure of structure members is rare. Most of the time, you will never see failure in the member itself. But most of the time, your failure happened in your connection. It's the weakest part in your member. So, most structure failures are the results of poorly designed or detailed connections. Modern steel structures are connected maybe by welding, bolting, and your bolts may be high strength bolt or common bolts, or by combination. You have weld, you have bolt. Old fashioned was rivets. If you can watch very old bridge, steel bridge, you can see this type of connection, which called rivets. But nowadays we are using bolts. You have hole, and during this hole we have bolt and nuts. Welding of your member, or maybe a combination between welding and bolts. If you have, let's start first with the bolted connection. If you have bolted connection between two members, this plate or this plate, we have a connection in between. What is the mode of failures? What do you expect of failure between or at this connection? What do you think?
Shear bolt.
Actually, we have two main kinds of failure. The first mode of failure, failure in the bolt itself. Your bolt is weak, so you have shear off in your bolt. So first one, failure of the fastener. Second one, we don't have any failure in the bolt, but failure in the connected parts. We have two steel plates. Maybe you have fracture in the net area. Do you remember? We covered this one. During your design of tension member, we have two conditions. The first one, hey, we need to avoid what? Yielding. Do you remember? So 0.9 F yield area gross. Second condition, we need to avoid fracture of your member. So point what? 0.75 F ultimate area effective and this area effective coming from area net, this case to avoid this mode of failure. In the net area, maybe the effective net area, we need to avoid this kind of fracture in the material of the connected members. The second one and third one, we will talk about this today. Tearing or bearing failure. Maybe the fracture will not happen like this, but maybe part in front of your bolt will be teared. Fracture or shear out at this location only. Or no fracture will happen, no shear out, but bearing failure. You have excessive elongation in the hole around your bolt. Something like this. Can you watch this? Successive deformation of your hole. One more time. We have two main mode of failure in your bolt connection. The first mode of failure, shear off of your bolt. Fracture in the bolt, in the shank of your bolt. The second mode of failure, failure in the material of members connected. We have two members connected. You have net tension. You have tearing behind the bolt. You have bearing failure in the material of the connected members. So we covered this mode of failure during your design of member. That's right. So we need to avoid three types of mode of failure. The first one, we need to avoid any fracture in the bolt. We need to avoid any tearing in this part of your member. We need to avoid any excessive deformation or bearing failure in your material. So at the end, we have one condition, one condition, one condition, one condition, one condition to say finally, hey, my member is safe, my connection is safe. For example, maybe we have a member, single angle or double angle. This member at this location can support 70 kips. At this connection, your member can support 60 kips. At this connection, maybe welded connection, on the other side of your member can support only 50 kips. So finally, this member in this truss can support how much load? 50 kips.
The load.
So the final decision on the capacity of your member not only related to the member itself, but also related to the connection of your member to avoid any undesired mode of failure. Any questions so far?
I have a question.
Yeah.
All these modes of failure are due to tension. Is there any type of failure due to compression?
You can expect also bearing and compression. It doesn't matter your member coming in this direction or this direction. You can expect this type of failure, excessive deformation on the hook. That's right. For tension or compression, it's okay. You can expect also fracture in the bolt. Maybe we don't have this one or this one. Okay, but we still have bearing failure and we still have shear off or fracture in the bolt.
Thank you.
Yeah. It's very simple, but we need to understand just the steps we need to follow for your design. One more thing. Sometimes your connection called single shear, sometimes called double shear. What is the difference between single shear and double shear? Single shear, you have one plate and another plate connected together with your bolt. So how many planes in the bolt will be sheared off? I think you can expect fracture at this location. That's right? So we have only single plane. So it's called single shear. If you can draw free body diagram for your bolt, the upper part related to the first plate under the effect of this force B. The lower part of the bolt related to this plate under the effect of P. So if you would like to get your stress here, it will be P divided by area bolt. Area of the bolt. However, if you have three plates, this one and this one, in this direction under the effect of P, and the third one in this direction under the effect of P. So how many planes in the bolt will be under the effect of fracture? Maybe this one and maybe this one. If you would like to draw your free body diagram of your bolt, the upper part under the effect of P divide 2. The lower part under the effect of P divide 2. The middle part under the effect of P. So at this location, what do you have? Your stress will be P divide 2, the force on this bar divided by area bolt. Area of the bolt. Which stress is lower and which stress is higher? Area bolt is the same for this bolt in this case and this bolt in this case. But the denominator, we have here P, we have here P divide 2. So which stress is the lower one? We prefer this one. We prefer double shear failure. So the addition of more thickness, more layers of your thickness, 1, 2, maybe 3, maybe 4, of material to the connection will increase the number of shear planes, double shear, triple shear, and further reduce the load on each plane. That's fine. Reduce the load means reduce the stress on the bolt. However, that will also increase the length of your bolt height. I think that this length may be more than or greater than this length. That's right. So longer bolts, we don't like longer bolts because longer bolts, the fastener will increase the length of the fastener and become subject to bending. We can expect bending on the bolt. Anybody can conclude anything from this case and this case? Yeah. Sometimes your member is single angle. So if you have single angle, one angle, your bolts at this location connected to this plate. So what do you expect? Is it single shear or double shear?
Single shear.
If you have double angle, we have one angle here and we have another angle there. And in between we have your plate. and you have bolts here. So if you have double angle connected to gusset plate, we have double shear. So we can expect this connection is stronger than this connection. So we prefer our members to be double angle, double channel, something like this to improve the behavior of your connection. Anyway, we have something called single shear. We have only one plane in the bolt under shear off. Double shear, we have two planes in the bolt under shear off. We added many thickness of the connected material. We like double shear case more than single shear because in this case the plane of the bolt will be under smaller value of load. However, increasing the length of your bolt will be subject to bending. Any question so far? Any question? We need to understand what's going on. Then, okay, now I can figure out, hey, yes, we have a bolt. We can expect tearing something like this in this little part of your member behind your bolt. We can expect bearing like this. So can you tell me, we need to avoid this mode of failure. Can you tell me what is the resistance of your member to avoid all of this stuff? Yes. Finally, without any introduction, your nominal resistance of your connection to avoid this tearing behind the bolt, behind the edge bolt. It is the edge of your member. Equal 2 times 0.6 F ultimate LC times T. So finally 1.2 F ultimate LC times T. Okay, I understand what is the value of F ultimate based on the type of material. My question